Alrighty, so what we've just discussed is the fact that the speed of light is constant. Everybody measures the speed of light to be the speed of light. And we'll talk more about that later, some of the ramifications of that. But now we want to kind of shift gears, and we want to talk about simultaneity. Say that fast 10 times. Simultaneity, it's referring to simultaneous events. Okay, so basically what we're doing is we're investigating time. We're investigating the properties of time in two reference frames. And don't forget, we're always going to use this. We're going to have this S prime moving with respect to S. So S prime moves with velocity v with respect to S. And we don't know anything about S. Could be at rest, doesn't have to be at rest. We don't care. We just know that this guy moves relative to that guy. Okay, so let's talk about simultaneity. All right. Oh, yeah, I already said that. Yeah, I'm sorry. Okay, simultaneity. So here we go. Here's a rocket. And the astronaut places these two light sources right in the middle of the rocket. So here's a target or a light detector. Here's a target or a light detector. So this distance equals that distance. Okay? All right. Now, when you hit the switch, these two light sources go, all right, so the two light sources emit a pulse of light at the same time. All right? So, according to the astronaut, well, I mean, here's the question. When do these pulses of light hit the detectors? Right? That's the question. Okay, so here, now remember, I forgot to say this, sorry. The rocket's moving, All right. So the question is, when do the pulses reach the targets? So we want to look at different reference frames. So first we'll choose the reference frame of the astronaut. Well, the astronaut is not, the astronaut's in the rocket, and the astronaut is stationary in the rocket. So as the rocket moves this direction, the astronaut moves with the rocket. So the astronaut just sees this one hit and at the same time as that one. Sort of makes sense, right? Okay, so the astronaut, according to the astronaut, the two pulses of light emitted at the same time at the center of the rocket will arrive at the ends of the rocket simultaneously. I think you have to agree that makes perfectly good sense. All right, fine. But how about the mission controller, the guys back on Earth? So this is what it's going to look like to somebody on Earth. So, okay, so bingo, the lights flash, right? Okay, the rocket is moving to the left. So which pulse is going to hit the target first? Remember, the rocket's moving this way. Well, this pulse is moving that way, right? So which one's going to hit first? Obviously this one, right? Because this target is moving toward the pulse of light. This target is moving away from the pulse of light. So what's the mission controller back on Earth going to say? According to the mission controller, the two pulses emitted at the same time from the center of the rocket do not arrive at the ends of the rocket simultaneously. So what's the conclusion? I mean, the conclusion is two events that are simultaneous in one reference frame are not simultaneous in a different reference frame. Now remember, when I'm saying a different reference frame, I'm saying a reference frame that moves relative to the first reference frame. Okay? So there you go. So whether or not two events are simultaneous depends on the state of motion. So simultaneity is not absolute. It's relative. Okay? It's another relative concept. All right, so which of the following statements about simultaneity are true? So everybody pause your video and read it and figure it out. Okay, you're back. Which are true? Two events cannot be simultaneous in two different reference frames. That's the whole point. Right? They will be simultaneous in one reference frame, but if one reference frame is moving relative to the other reference frame, and that's what we mean by different reference frames, they cannot be simultaneous. That's weird, because we don't see that on the Earth, right? Okay, now this is an awesome video clip, which we're not going to watch here. So please watch this on your own. So go to Canvas. I think I have a module called Videos or something like that. It's not the online module, it's a video module. And there's a simultaneous events video clip, just real short, but please watch it. It will help you understand this whole concept. Okay, now we want to talk about time dilation. So you know earlier we said that delta t was not equal to delta t prime? Well, now we're going to work out the math. Okay, so here's what Einstein, this is a super paraphrase. Time is a physical part of the physical universe. Just as one can measure the properties of a stone or a beam of light, one can measure the properties of time itself. Now that's kind of weird, don't you think? Measure the properties of time. Well, that's what we're going to do. All right, here we go. So how do you measure time? Well, I mean, the easiest way is just to use a clock, right? Use a watch. Okay, now think about it. We want to, you know, we're discussing time in two different reference frames. So we want to have a clock that's incredibly simple. We don't want any like mechanical problems or friction. We just want to have a simple clock with not any problems. So here's our simple clock. This is called a light clock. And it's simple. All you need is a mirror here, a perfect mirror here, which is not simple, a perfect mirror here. These have to be perfectly parallel, and they have to be 150,000 kilometers apart. So obviously this is not a simple clock. But it is. I mean, conceptually, this is a simple clock, right? You just need a mirror in a mirror. Okay, it's a little difficult with that, I agree, but still. And then what you have a light source here, and it has to shoot the light perfectly perpendicular. Okay? Now, why did we choose 150,000 kilometers? Well, because the speed of light, you know, I always write it like this, right? Well, it's also 300,000 kilometers per second. Okay? So, with this super cool light clock, you know, you press the button, and it goes up and back 1 second, up and back another second, right? Because it travels 300,000 kilometers in a second. And this is half of that, 150,000 kilometers, right? So awesome light clock. 1, 2, 3, you know, seconds. All right, so there you go. Now, how are we going to use it? Okay, so again, two reference frames. So don't look at this yet, right? Just look at this. Okay, now this is Velma. She must be pretty big, because remember, this is 150,000 kilometers. Just kidding. So she's in her own rocket ship, right? And so the light clock is stationary relative to her, right? You know, relative to her, there's the light clock right there. So according to Velma, you know, she pushes a button, 1 second, 2 seconds, 3 seconds, you know? Okay. So that's pretty simple, right? So just keep it simple. 1 second, all right? Just one round trip, up and back, 1 second. Now let's look at it from the perspective of Mort. So Mort's on the Earth or whatever, some weird planet, I don't care. And you know, Mort sees Velma traveling to the right. So, what does Mort see? Well, you know, Mort sees the light. It doesn't just go straight up and down. It goes like this. Right? I mean, think about it. Let's do it with me. So according to me, the light would just go like this, right? But now if I'm moving relative to you, what does it do? It moves in a triangle, right? It goes like this. Yeah, okay. Now, obviously, if this is 150,000 kilometers from here to here, well, what is it from here to here? Well, it's obviously more, right? It's longer. This is greater than 150,000 kilometers. Agree? Okay, now remember, everybody measures the speed of light to be the speed of light. So Velma says the distance is 300,000 kilometers. Speed of light, 1 second. Mort says the distance is greater than 300,000 kilometers. Same speed. So therefore, the time to do this is more than 1 second. So, Velma, so again, we're just concentrating on Velma's clock, right? Okay, so Velma's clock. Velma says 1 second, right? Zoop, zoop, 1 second. Mort says, you're nuts. Mort says it traveled more than 300,000 kilometers, traveling at the same speed. So Mort measures more than 1 second on her clock. So Mort says, Velma, your clock is running slowly. You know, for example, he'll say, maybe it was like 1.5 seconds, but Velma says, no, it's a second. So Mort says, your clock is running slowly. Okay, now let's switch reference frames. Now we're going to say that Mort has the light clock. So, so Mort, 1 second, right? But again, Velma is moving past him. So what does that mean? Well, what does Velma see? Velma says she's stationary, so she sees Mort going that way. So Velma sees the light, same thing, triangle. So Mort says a second. Velma says more than a second. So, okay, so now we're focusing on Mort's clock. Mort says 1 second. Velma says more than 1 second. So Velma says, Mort, your clock is running slowly. So here's the situation. Mort says, Velma, your clock runs slowly. Velma says, Mort, your clock runs slowly. Now, how can that be? Well, who's correct? Well, here's the fun part. They're both correct. Now, how can they both? How can that be? How can that be? Time is relative. All right. If you're in a moving reference frame, you're going to measure a different time. Time is relative. All right. Now, here's the fun part. The time that Mort measures on Velma's clock depends on the speed of Velma's reference frame relative to Mort. Woohoo! So here's a graph. Okay, so let me repeat that. The time that Mort measures on Velma's clock depends on the speed of Velma's reference frame relative to Mort. So this is an incredibly important graph. So this is the speed, in terms of the speed of light, of Velma's rocket ship. So 1/10 of the speed of light, 50% of the speed of light and on. And this is, okay, so 0. So this is what everybody would measure, right? 1 second, right? If Velma was not moving, both Velma and Mort would measure 1 second. But notice, as Velma starts going faster and faster, what happens to the speed? Remember, Velma's always measuring a second, but Mort is measuring longer than a second, and it depends on the speed of the rocket. So look, if the speed of the rocket is half speed of light, then Mort would say, like, just a little less than 1.2 seconds. If the rocket is going 0.9 c, 90% of speed of light, then Mort would say 2.2 seconds. Again, Velma says 1 second, but here it would be 2.2 seconds. You can see as you get closer and closer to the speed of light, it gets longer and longer and longer. So there it is. So this is like your t and your t prime, right? Velma always says 1 second. Mort says something completely different, but it depends on the speed. It depends on the speed. Now this is just a graph. We still have to get the equation, but this is still pretty cool, right? Okay, let's see. Oh yeah. So people always say, well, how come we don't ever notice this on the Earth? Well, this is 1/10 of the speed of light, right? So this is 186,000 miles per second. So 1/10 of the speed of light would be 3 times 10 to the 7th, which would be 30 1,000 kilometers or 18,600 miles a second. We don't have anything that goes that fast. We don't have anything that goes anywhere near that fast. So our fastest missiles, anything, we're down here. And if you want to convince yourself of that, so this is a website on Wikipedia. It's the list of vehicle speed records. So just go to this website and you'll see what the fastest Earth-made objects are. And you can easily convince yourself that the fastest speeds of anything that we can make, rockets and missiles, is nothing compared to the speed of light. So we're down here. Okay, so now we want to get the equations, right? We want to actually figure out the equations that relate the two times. And it's just algebra, believe it or not. All right. So this is, okay, so this is the Mort and Velma thing. Okay, so Mort's standing on the Earth. Velma's going by, right? Velma is moving relative to Mort. So this is Velma, frame S prime. So Velma just sees the light go straight up, straight down, right? Okay. Now here, we're just going to call it H. We're not going to call it 150,000 kilometers like we did last time. We just want to be general, okay? Why not? Doesn't hurt. Okay, so let's see. So for the light to go up and back, the distance is 2h. So okay, so we have distance equals speed times time. So the distance is 2h. The speed is the speed of light. And the time is speed of light. Time. We're going to put a prime, right? Because it's frame S prime. So distance equals speed times time. Delta t prime. So therefore, delta t prime equals 2h over c. We're going to use that in a couple of minutes. That's why I'm making a big deal about it. Okay, now, I'm going to write that up here. Okay, now so that's speed, that's a frame S prime. Let's go to a different one. Let's go to what Mort sees, right? This is frame S. So now this is what Mort would see when Velma is zipping that way, okay? So now, Mort sees the light going like this. Well, okay. So we got to get an equation. Well, we can do it. Now remember, the rocket ship is moving to the right with speed v, right? Okay, so, and we're saying the time from here to here is delta t. So this distance, right, the clock moves a distance, v delta t, right? Distance equals speed times time. So this distance here is v delta t. Well, let's just look at this right triangle. Okay, this is h, no kidding, that hasn't changed. This is 1/2 the base, so it's 1/2 v delta t. And this, remember, speed of light is speed of light, right? Speed of light is the speed of light, right? And so this distance, it's c times the time, right? Remember, the time is from here to here. So this is only half the time. So this distance is the speed times the time, c times t over 2. All right, so let's use Pythagorean theorem. So for frame S, we're just going to use Pythagorean theorem. So this squared plus that squared equals that squared. So v delta t over 2 squared plus h squared. Okay. Now, so that makes good sense, right? That squared plus that equals that squared. Okay. Now, this is the time for you to do some work. And please do it. Don't just wait for my results. So what I'd like you to do is, remember, we're trying to compare the t's, right? Delta t with delta t prime. So please solve for delta t, okay? And I want your answer to be in terms of v divided by c. All right, so pause your video and do it, all right? Please, please do it. Okay, so I'm assuming you did that because it's good. You need to do these kinds of things. So here's the answer. So all you do is algebra, you know, not a big deal. So you get delta t equals 2h over c all over square root 1 minus v over c squared. Okay, that's what you should have gotten. And that's the same thing as delta t prime over square root 1 minus v over c squared. So make sure you can do that. I mean, you should be able to do that. So what does it say? It says what we've said before. It says that delta t is not equal to delta t prime. People in different reference frames measure the same thing, get different results. Now, you're going to see soon enough that whenever you're doing relativity, you see this v over c all the time. So you get really sick and tired of writing it. And so people that do relativity for their profession, or like people that use it a lot in particle physics or whatnot, we've come up with a bunch of abbreviations just to save trouble. Okay? So here's an abbreviation. So what we say is we say that beta equals v over c. So we're not going to write v over c anymore. We're just going to write beta. And you think it's a waste of time, you wait. Now, let me write this. Let's write this. Isn't this the same thing as 1 over square root of 1 minus v over c squared times delta t prime? Yeah, it's the same thing, right? Okay, so you're going to also see this thing all the time in relativity. And the same thing, you get sick and tired of writing it. By the way, this is the same thing as 1 minus beta squared, right? So you get sick and tired of writing this thing. So you define it to be gamma. So gamma is 1 over square root 1 minus beta squared. If you're really lazy, you can just write that as 1 minus beta squared to the negative 1/2 power. And I promise you, you're going to use this all the time because they're just fundamental. All right. Okay, now notice, look at this gamma. So beta, you know, beta is v over c. So for things that are not light, this is always going to be less than 1, right? So 1 minus something less than 1 squared. So this thing here is going to be less than 1. Well, 1 divided by something less than 1 is going to be what? It's going to be greater than 1, right? So gamma is always greater than 1. That's a good little thing to remember because you can check your work. All right, so now let's write this. Let's just summarize. So what we've said is that delta t equals gamma delta t prime. So delta t is not the same thing as delta t prime. Now, for some reason, which I don't know, I like this, but some people, like Randy Knight, write it like this. Gamma delta tau. Huh? Greek letter tau. So they say that delta t equals gamma delta tau. Now, you have to understand the difference between delta t and delta tau. And so to make it easier, we give them names, and you have to understand the names, or you're not going to be able to solve any relativity problem. All right? So delta tau, this thing here, it's called the proper time. And talk about a really bad name. There's nothing proper about it. It's just a name. It's just like George, okay? But there's nothing proper about it. But this is what you need to understand. The proper time in a particular reference frame is the time interval between two events that occur at the same point, the same position in that reference frame. We'll do some examples, don't worry about it. But that's what you want to remember, right? So whoever measures, okay, so the proper time, you have both events occurring at the same location in that reference frame. Just understand that. And I already said this. Okay, so that's the proper time. And this is called the dilated time. Dilated time. It's called time dilation, right? And again, this is longer, right? Because this is bigger than 1. So delta t obviously is bigger than delta tau. But the longer dilated time is the time interval between the same two events as measured in a second reference frame that has a speed relative to the first frame. No kidding. The two events will be at different locations in this second reference frame. And we'll do some examples. And yeah, here's why they call it time dilation. So if you ever go to the optometrist, you know, they dilate your eyes. So here's undilated people, here's your dilated people, you know. Okay, whatever. So it makes it easy to remember, right? Okay, so, oh yeah, before I do some examples, you know, we derived this equation using a light clock. And we did that just because a light clock was simple. I mean, you know, and I mean, it's simple, just simple, right? They didn't have a lot of moving parts. But remember, we're actually talking about time. So it doesn't matter what kind of clock you use to do the experiment. Light clock, I don't care what kind of clock. We're talking about time. We're discussing the properties of time, okay? So it doesn't matter what kind of clock you use. Time is relative. Okay, let's talk about this proper and dilated business. Okay, so this is according to Mort, right? Well, okay, I mean Mort and, okay, anyway, sorry. According to Mort and Velma. So see, Velma, remember, she's in her little light clock, right? So she presses the button, the photon leaves the floor, goes up, comes back. Now, that's what she sees, right? So according to Velma, you know, the photon leaves, returns. So if this is event 1, the photon leaves. This is event 2, the photon returns. Both of these events are at the same location according to Velma, right? I mean, let's pretend I'm Velma. So right there, so at my foot, photon leaves, photon returns. According to me, in my rocket ship, both events happen at the same location. First event, right by my foot. Second event, right by my foot, at the bottom of the light clock. All right? So, all right, so that's the thing. So I guess to answer this question, first you have to say, what's the first event? What's the second event? Okay, obviously. Then you have to say, okay, which reference frame did the events happen in the same place? Well, obviously Velma, right? Okay, now Mort, where did the events happen? According to Mort, this event was way over here. This event was way over there, right? So Velma measures the proper time, and Mort measures the dilated, the longer dilated time. Okay, that's a good place to stop. You know,